Check it out now, y'all.
NanoHub U, online instruction.
Hi, we're back again to discuss the solutions to the week three homework problems. This particular discussion is focused on problem number 1, and this problem is a simple problem about a tip of radius r sub tip brought into contact with a substrate, flat substrate. And in this particular problem, there's the air that surrounds the tip substrate contact. That air is contains some water vapor, right? So there's molecules of water that are floating around in the air. And these water molecules will produce a thin coating of water on both the tip and the substrate. And furthermore, when the tip comes into contact with the substrate, these water molecules will condense into this contact region until a stable water meniscus is formed. So in this problem, we're assuming the relative humidity of the ambient air is 40%. So that's a number that we're going to use to evaluate various quantities in the calculation. The water meniscus has to be characterized by the radius, the surface of the water that condenses has to be characterized by 2 radii of curvature. And these 2 radii of curvature are indicated by the parameters R1 and R2. R1 is the radius of curvature of the very tight surface that forms between the tip and the substrate. The location of the center of this this circle that defines the radius R1, that location is outside the water meniscus. Because it's outside the water meniscus by the sign conventions, R1 is going to be assigned a negative number, so R1 is going to be less than 0. The other radii of curvature is the circumferential radius that describes the macroscopic size of the drop. R2 is going to be considerably larger than R1. The center of R2 is located in the inside the liquid, so that means that this radius of curvature R2 is going to be greater than 0. It's going to be a positive number in the statement of this problem. So that's something to keep track of as you work through this. There's a sequence of questions that are asked. The first question is, what determines these 2 radii of curvatures, R1 and R2? And hopefully, if you listen to the video lectures, you'll recognize immediately that the answer here is the Kelvin equation, and I believe that's choice C in the problem statement. The second question to this problem is what is the sum of 1 over R1 plus 1 over R2? And to solve that, to answer that question, we have to use the Kelvin equation, which I write down here on the first line. It's customary to rewrite the sum of the reciprocals of the 2 radii R1 and R2. It's sometimes convenient to rewrite that as 1 over R sub k, where R sub k is referred to as the Kelvin radius. So if we want to solve for what 1 over R sub k is, we have to evaluate these constants, gamma, the molar volume of water, the universal gas constant, temperature T. This natural logarithm of the pressure above the curved surface divided by the pressure above the flat surface, that quantity is identified with the relative humidity. So the relative humidity of 40% is used to evaluate the natural logarithm of these 2 pressures. First thing I calculate is the constants in this problem. So gamma is the surface energy of water. It's 72 millijoules per square meter. V is the molar volume of water. That's 18 cubic centimeters per mole. R sub gas is the universal gas constant. That's 8.314 joules per Kelvin mole. T is the absolute, is the temperature in absolute degrees Kelvin. That's, in this case, we'll just pick 300 Kelvin. We have a units problem here. We have to convert centimeters to meters. So I include this factor that'll give us that conversion. And when I work all this arithmetic out, I end up with a number here that's about 0.52 nanometers. I can then use that number in this equation, to solve for R sub k. And so R sub k in nanometers is going to be this quantity 0.52 divided by the natural log of this ratio, which is 0.4. When I evaluate that, I get a number that's like minus 0.57 nanometers, right? So the minus sign just means that the 1 over R1 term here is going to dominate over the 1 over R2 term. That just simply means R1 is much smaller than R2. Since R1 is a negative number, that's how you interpret that negative sign. And I think the correct answer in the list of answers given in the problem, I think the correct answer is B. The third question, let's see, what is the third question? The third question asks, what equation determines the pressure difference between the water vapor outside the meniscus and the pressure inside the meniscus? So there's a partial pressure of water outside. There's a pressure of the water inside. The difference in those two pressures is determined by the Young-Laplace equation. So the correct answer for question 3, if you listen to the lecture notes, hopefully you would be able to immediately write down Young-Laplace, right? And I believe that's choice B in the statement of the problem. The Young-Laplace equation states that the pressure inside the water drop minus the pressure outside is equal to the surface energy gamma times this parameter that we just calculated in part 2, 1 over R sub k. So gamma again is 72 millijoules per square meter. R sub k we calculated as minus 0.57 nanometers. So when I evaluate this expression, I end up with minus 0.13 newtons, minus 0.13 times 10 to the 9th newtons per square meter. 10 to the 9th newtons per square meter is a gigapascal. So I get a pressure difference between the inside and the outside of about 0.13 gigapascals. The negative sign just indicates that the pressure outside is going to be greater than the pressure inside. And I think you can almost guess that just by the radius, the shape of the radius of curvature here. So recall if the pressure outside and the pressure inside are the same, this interface would be a straight line. And then depending on which pressure is greater, the interface, the surface of the interface will either be pushed in or pushed out. So the way I interpret this negative sign is that the pressure outside is greater than the pressure in. And of course, that's what we anticipated when we drew this diagram to begin with. So that's how I think you solve the questions asked in problem 1.